Okay. Oh, there's a new live transcript feature. I'm going to turn that on that Zoom did. Okay. Let me see. Enable auto trans. I'm going to do this. Let's see if this works. Oh, cool. It works. It's showing up on the bottom. This is so cool. It's so distracting, though. This is going to be awful for me. All right. And whatever. Just my ADD wasn't bad enough. Okay.
Do you really have ADD? I do. That's the only reason I'm asking.
I do. It's terrible.
Yeah. Okay. I feel your pain.
It's a lifelong struggle. Anyway, okay. So again, welcome to our pajama party. Not the greatest participation so far, but hey, I'm hopeful. I'm hopeful we'll have some people coming in, last minute entries. A reminder, course website here. We've got lecture notes, course materials, everything there. Let me know if you need the link. Let's see. Then we've got project 1 is done. I hope wasn't too bruising. We're going to talk a lot about that. Homework 1 is due next week. We're going to talk about a bit about that today. And we're also going to sort of tease up project 2. Then I also just kind of wanted to throw out a quick reminder for Secret Bruin. If you guys are interested in participating, we are going to kind of cut off. We're going to start assigning Bruins this weekend. So if you're interested in doing it, please submit for it as soon as possible. So yeah, please remember to do that. And then just the student directory as well. If you guys are just kind of looking to connect with peers, take a look, see what other people have written, please submit for that as well. So we put out a link. I sent out an announcement on CCLE. So there's under the announcements, you should have gotten an email about it too. But yeah, let me know if you, Neil, if you can't find it, let me know. And maybe I'll try to paste it into the chat before the end of the class. Yeah, and I also wanted to say, I went back and looked at the transcript from last week and you guys are hilarious. I missed some of the comments you guys made about birds and it was just, oh man, it was amazing. You guys are amazing. I love the vibe last week. So I did just want to acknowledge that. Okay, so I'm going to stop sharing. You know the drill by now. It's going to be our pajama party. You got your jammies. Let's rock them. Let's see, this is going to be a contest. So if you are, okay. Oh, thank you, Neil, for posting in the chat. If you're participating, turn on your webcam, put yourself in the chat. You know the drill, name and what you're rocking. And then the rest of you get to vote. So turn off sharing. Where is my, can you guys see my screen still, or what happened here?
We just see you.
Oh, okay, cool. Okay. Oh yeah, somehow my Zoom. Okay, so let's see. Who do we? Okay, Rishab coming in. Is that what is that?
It's a Yoshi onesie.
Oh, nice. Okay.
See the eyes up here.
Awesome. And then I see Isabel, you're rocking a Taylor Swift. Is that concert tee or what is that like legit?
I just found it on Etsy. It's like all of her eras. So we have Fearless Taylor and Reputation Taylor and Vogue cover Taylor. It's every single Taylor you could possibly want on one shirt.
Taylor is a very multifaceted artist,
She does it all and she does it so well.
She has layers. She's got depth.
She really does.
Okay, let's see. Who else do we got? Okay, not a lot. And don't pretend like you guys haven't been wearing pajamas your entire quarter here. Some of you gotta have some awesome onesies. I almost wore my Pikachu onesie, but I went with this one instead. I don't know if I'm having regrets about that. I only get like one session a quarter when it's socially acceptable to wear a onesie to class. So it's like, it's a big deal for me. So No, you're not allowed to vote for me. Okay, so I think it's down to Rashab and Isabel. We got a head-to-head contest here. So put your votes up. Oh, I need somebody to tally the votes. Can somebody be the official vote tallier?
I don't think we need to count.
Okay, even though you're right, that kind of hurt a bit. That kind of hurt a bit.
Hey, I said your shirt was fire.
Okay, I'll allow it. Because it is. Look at it. There's like 8 Taylors. Ugh.
Swizzle in the hizzle. I don't know. We're seeing some votes. You see, you jinxed it. Isabel's making the late comeback. I think we're going to need to get a tally after all. I think someone started taking their victory lap a little too soon. Okay, I need somebody to hop in here and tally these. Can somebody please do that for me?
I'm attempting to count, but someone else should back up tally.
Yes, our electoral integrity is at stake here. It's a lot of responsibility. I mean, if you lose faith in our informal Zoom chat process, you know, what hope is there for our future? Okay, last call. Last call for votes. Okay, Neil's got a tally. Uh-oh, we've got conflicting tallies. Okay, we have 3 separate tallies. Okay, no more votes, please. Nobody submit the votes. And you can self-vote. I'm not gonna
do a Zoom poll or something.
The problem is you have to pre-script those.
Well, what you could do is like make a Zoom poll that's just like 2 choices, like A and B, and then after a bunch of people vote, you take the 2 people with the highest votes, and then you say like click A for this person, click B for this person.
Shoot,
and
that's
the final
smart.
decider.
Spencer, that's a good call. Okay, that's what I'm gonna do in the future. Whenever we do these in the future, I'm just gonna do, you're right, I'm just gonna do a maybe like a B, C, D, and then just have votes. Okay, that's a good call. Okay, but we do need, okay, somebody in the chat gonna have to recount this, and we're gonna have to come to a decision here on who actually won this contest. But you see, you know, the pundits called it early. The mail-in ballots were still coming in, you know. You looked at those early exit polling results and you called it too soon. Okay, so let me know when a decision has been made on who actually won this, and they will receive their duly earned reward. Okay, back to the slide. Okay, so we are doing. So what I'm hoping to run through today in brief is I want to run through a coding sample, both to kind of consolidate some of the work we did with project 1. Maybe, you know, now that you kind of raced, I know that the scheduling for that was a bit chaotic and crazy and all that jazz, but like hopefully we can kind of take a step back, walk through all the steps, maybe help to facilitate, you know, a little bit more of an understanding. And then we're going to kind of use that to then pivot into project 2. And so as I mentioned in lecture, the kind of the big, we're going to go over in more detail, but the big shift from project 1 is that project 1, you were building a predictive model. So your output would be a continuous variable. You know, it could be a number of values. For project 2, you're going to do a discrete classifier, and specifically you're going to do a binary classifier. So it's a yes, no, 0, 1. It either it is or it isn't. And to do so, we're going to do a topic near and dear to my heart: avocados. In fact, I will tell you, this whole lecture day is going to be like very LA themed. I didn't mean to do it that way. It just kind of worked out that way. But we're going to start with avocados. And so, yeah, the Jupyter Notebook, the data, it's available here. It's available on the site too. If you want to just kind of grab the link, you can download them and sort of work along if you want to. And we're going to do sort of we're going to use the same exact data, but we're going to run 2 models. We're going to run a predictive regression to predict the average price of an avocado. And then we're going to run a classification exercise. So we're going to try to predict whether or not an avocado is organic or conventional. So, oh, okay, you guys need the link? Sure. Okay, well, so where do I have? Well, okay, so here's the link. I'll just send you the link directly. In the chat. Okay. So then go back to slides. Okay. So let's actually pull up the thing. So if you pull it up, it will look something like this. So here is a data dictionary. When we look at our data, and we'll pull up the head, so we'll see it in a moment. But we've got date, which is the date that this data is observed. We have the average price of a single avocado on that given day. We have the avocado type, conventional or organic. And again, that's going to be our classification variable. So we'll come back to that. Year that this is recorded. Region. So this is the specific city or region in which this is observed. Total volume will tell us the total volume of avocados sold. And then these are specific sort of avocado types. So I forget what PLU stands for, but these are different sort of so you might see like maybe it's a medium Haas, a large Haas, extra large Haas, or whatever, those particular avocado types are. So to start out, we're importing we're going to NumPy and pandas. Then we're going to read in. This should all be kind of muscle memory for you guys. At this point, we're reading it in, and then we're just going to call the header function. So now we can see this again. So we have an index, an unnamed index ID. We have the date the observation takes place, the average price during that day, total volume sold. These are those 3 product types. We have the total sales in terms of baggage. So small, total bag, small, large, XL, the type, year, and region. And then as the next step, we're just going to call info on ours. So remember, we talked about this, and quick slide about this, but remember, when we're actually plugging our data into our learning model, only instant float types can be input into our learning models. So info will give us kind of a quick thing. It looks like we're pretty good with that. The only things that may give us a problem are going to be date. That's an object form. Region is an object, and type is an object. Okay, so that's not great. One thing, I don't think I have this even in the code. I think I just, yeah, did I? Oh, okay, I did. Okay, I did do this here. One thing I'm going to note here, and we're not going to necessarily use this, but it's kind of a cool thing that you can do with pandas that can be very helpful, particularly when you're doing feature engineering, is Python does have a date time thing, some data type, and so you can do a conversion to that. So it's already in a good format for that. So you can do a to date time method and convert that, and you can see then if you pull the info now instead of object, it's that date time, and that can be incredibly useful when you're trying to do things like feature augmentation. So you may want to aggregate over certain regions or certain time frames. You may want to do some statistics based on time. If you're doing time series analysis, this can be really helpful, because if it's just in object form, it's not really kind of useful from that perspective. So just want to know that we're not going to kind of go down that, but just to be aware that that is something you can do. let's see, another thing we're going to look at here is we're going to just look for data is null. Now, one kind of interesting thing, if you're just calling the info thing, it will already give you a non-null count. So as you can see here, all these features have a nice 18,249 non-null values. And so that already tells you this data looks nice and cleaned, but we can do a nice thing where we can do a is null and sum for the entire data frame, and it will return a count of that. And indeed, we don't have any null values, so no need to worry about imputation in this instance. So, okay, so all of that's looking good. Do I have anything in the slides I need to mention? Yeah, so again, just daytime, some things you can do with it. It's kind of fun. Okay, let's run through it and then I'll come back to that. So then let's look at building a predictive model for average price. So if you'll recall, we have, in this case, data average price, that's going to be our Y. Those are going to be our labels. So for every feature here, we have this average price. That's what we're going to try to do a predictive model for. Okay, then we're going to drop our labels from our features. This is kind of a very important step you want to do. It's something that is kind of intuitive, but you would be surprised that doesn't always necessarily happen. Don't leave your labels in your features. Again, something you would assume people would do, but people make that mistake. I've made that mistake an embarrassingly large amount of time. And some of you for project one may have ended up inadvertently doing that yourselves. Did some of you end up with like ridiculously low? Yeah, like did your mean square error almost equal 0 for project one? Well, chances are if that happened, it is a good chance you left your labels in your data. And then your linear regression model took one look at it and was like, hey, there's this one feature here that lines up just perfectly with the label. So, you know, I'm just going to set the coefficient to 1. I'm going to zero out everything else. And my God, it's perfect. Or nearly perfect, because you're still trying to fit a line. And even if you do have the label, it's never exactly perfect. But so I have had that happen where I've been running models and I'm getting these like amazing results and nearly perfect. I'm like, wow, this is great. My model's working perfectly. And I'll go back and I'm like, my labels are still in my features. So definitely make sure you're dropping your labels prior to doing your models. So we now have our X array, which is all of our features, and we have our thing here. So then let me just quickly do a double check on my features. Okay, so I have region, which is an object. Looks like object, and then type is also an object. So that's not great. So there are a couple of things we're going to want to do about that. So we're going to pipeline it. Here's a very, very simple pipeline that we're going to do. So the first thing I'm going to do is I'm going to set my numeric features. Those are everything that are not categorical. In this case, my categoricals will be region, which we said is here, and type, which we said is here. So those are going to be my two categoricals. The rest are numeric. For my numeric, since these are all already in sort of a good proper format, all I'm going to do for that is I'm going to scale it. I don't need to do an imputer because there's no nulls. So I'm just going to scale my data. And we're going to talk a little bit more about scaling it, but I'm just going to point this out for project 2, because project 2, one of the first things we actually have you do is we have you feed your raw data into a KNN model. And KNN, so you guys learned about this in lecture already. KNNs, they use Euclidean distance, right? You literally take, I mean, we'll go through all this, but you take the data that you're trying to assign a label to, and you literally look at relative proximity to other sort of data points in your data frame. And you say, whatever it's closest to, you essentially take a poll and you're like, oh, okay, it's this, great. I'm going to assign whatever that is. And so it is very, very, very sensitive to relative scale. If you have one sort of dimension that is in single digits and you have another dimension that's in the millions, and you're looking at just raw Euclidean distance, then clearly it's just going to look at the feature that's in the millions, because that's really the only thing that matters. Okay, there's a question in the chat. Floats. So I don't want to say either way. I think so the first thing is part of the pipelining, part of creating that NumPy thing is it'll do it for you automatically. So you don't have to do the explicit feature conversion. You don't have to do an as type conversion to it, because as pipelining, it'll do it for you. But if you just want to feed it in, like you can, so this is actually something I misspoke in office hours. You can feed in, as long as everything is either an int or a float, you can put a pandas array into it as well. And that'll work. And there are actually reasons why you may want to do that. And we'll kind of get into that a little bit. But from an efficiency standpoint, yes, it can help with your model. And particularly, for the purposes of this class, we're not dealing with data on the scale that you need to start thinking about those kind of efficiencies. This isn't a big data type course. All the models we're going to be building you can train on your local CPU. You don't need to think about these types of efficiencies. It's not a bad thing to think about them, because as you begin to scale, as you begin dealing with, commercial level type, enterprise type stuff, and then you may need to think about optimization strategies, but for the sake of this class, you should be okay without it. And then let's see, going back to my little pipeline here, but yeah, great question. And so then for my categoricals, I'm just going to do a one-hot encoder for them. And we're going to show in a second why that's not necessarily a great idea for me to do it, but I did it anyway. So I one-hot encode it. Here's my little NumPy array that outputs it. Everything is scaled. It's one-hot encode. Everything looks great. I'm going to do my train test split. I'm going to do an 80-20 split for that. And then let me just print the dimensionalities of this. And so, there are a few things that we want to look at just as a sanity check for this. So the first thing is, so this is my training features. This is my training labels, my testing features, testing labels. So the first thing you want to make sure is that the dimensionality adds up. So in this case, we have 66 features, and more on that in a second. And we want to make sure that there's a 1-to-1 ratio between labels and rows. So in this case, 14,599, great. 3,650. Okay, great. That's all looking good. Now, one thing that's kind of interesting here is like, whoa, where did that come? 66 discrete features, right? That sounds like a lot. And here is our perpetrator region. And do I do a discrete count of that here? Do I have a thing for that? Let me see. No. Okay, then I think, is that easy to do? So, well, I can try to type that out, but for the sake of time, you can, so if you do a distinct count of features, things, and you do it for region, you will see that in fact, there are 66 discrete regions as part of this data set. Or no, not 66. There are, if there is, I forget how many, but there are roughly 50 to 60 distinct regions that are included as part of this data set. And so when I one-hot encoded that feature, I ended up creating all of those features. And so that's clearly not great. And one of the things for homework one, when you're thinking about whether or not it's worth one-hot encoding your thing, is precisely thinking about just like how much it's going to explode your dimensionality. So, something again to think about with that. And that's a very thing you can do a count. You can call up a feature and you can just do a count method for it. And you can get the total number of distinct features and the associated values with them. But, so one thing you can do, for instance, if you wanted to keep that region, if you thought that was important, one thing you could try to do is try to aggregate those features. Maybe instead of, keeping it like we can see here, like we have Albany, we have West Texas, New Mexico. Maybe you can sort of group those together, cluster those together and say, okay, well, I'm going to do a Northeast, Midwest, Southeast, South, Southwest type deal. Like maybe aggregate my regions into a more manageable number of things. Okay, so there's a question in the chat about why dimensionality is bad. We are going to get into that in detail in subsequent weeks, but let me try to give you like the 30 seconds on it right now. But with the idea that we are going to kind of drill down into that. The reason it's bad at a high level is because of what's known as overfitting. So right now, there's this process, and let's use linear regression as an example of this. And again, we kind of haven't given you the full context of this, but right now, you give your model this training data, and you say, fit a model for it. You know, try to sort of optimize, try to create the optimal model based on this training data. And the goal with this is always to try and get a model that is as accurate, is as accurate as possible, but it doesn't overfit to that, because invariably the training data that you have, that subset of data, is not fully reflective of like the universe of data. There is sort of a universe of data that is out there, and then you have the sampling of it that has its own little quirks and statistical oddities and sort of variants that don't kind of fit nicely into the broader universe of data. And that really is the challenge of statistics more generally. You're taking this snapshot of the broader universe, and you're trying to use that snapshot to sort of model that broader thing. And so the problem here, and this is this balance, again, we're going to spend literally weeks on that, is trying to find that balance where you sort of fit your model enough to capture the general trends in the data, but you don't get so far into the weeds that you're capturing every, you know, all the noise and variance and random permutations in your data that aren't necessarily reflective of it. So what does that have to do with dimensionality? Dimensionality is essentially dimensionality. The higher the dimensionality, the easier it is to overfit. And the way of thinking about this at a very easy level is if you think about sort of the density of your data. So imagine, just to use a very crude example, let's say I have a one-dimensional array of 10 data points over a 5-unit thing. So it's 0 to 5, and there's 10 data points on it. So there I have a density of approximately 2, right? For every sort of unit on that thing, I have roughly 2 data points. If I then take that same data and I cast it onto a 2-dimensional space, so instead of a line, now I'm looking at like a rectangle, right? Suddenly my 5-dimensional thing becomes a 5 by 5, a 25 thing. And so my dimensionality, my density becomes 10 divided by 25. So already I'm looking at a much sparser data set. Then if I cube that, if I sort of take that same 10 points and I cast that onto a 3-dimensional array, now it's 10 over 125. And at that point, your data becomes so sparse, so spread out, relatively speaking, that it becomes much, much easier for your model to kind of cleanly divide that data, which sounds good. But again, it's precisely that sort of thing that leads to overfitting. When it's too easy for your model to say, oh, I can cleanly divide this, that becomes a problem. So long story short, when you sort of take your existing data, you explode the dimensionality, but you don't add any more useful information, which is exactly what we're doing in this case when we one hot encode it. You effectively sort of lead to that overfitting problem. And again, you don't have enough context to fully kind of conceptualize what's going on with that, but just that's in a very high level why that's a problem. So yeah, I'm sorry, that was a bit of a rabbit hole we went down, but okay. So does that make sense? I know I kind of chatted about that for a while, and I said it was 30 seconds, and 5 minutes later, you're still there. But yeah, for the sake of homework 1, it's just something to factor in. When you're thinking about the value of one-hot coding and feature, you know, it's worth thinking about the degree to which you're sort of blowing up the dimensionality of your feature frame. Okay, so all right, so we went through this, we pipeline. Okay, so then we're going to train test our model. So, and again, there's sort of some discrete steps here. So in this case, the first thing I'm going to do is I'm going to call, so I'm importing my linear regression thing. I'm going to call a specific example of it. I'm going to say, okay, this LM sort of stands for a linear regression model. That line is really just doing a shorthand. I could very easily just do model equals linear regression dot fit dot that, but it's just a nice shorthand for it. Now, model here, this is your actual sort of thing that you're going to train. This is your output, essentially. This is after you have trained your linear regression, you have come up with the coefficients associated with it. All that data is stored sort of in the model. So you call linear regression, you call the fit function, which is part of the scikit-learn thing, and it essentially says take your training features, take your training labels, and try to fit a linear regression model that minimizes the error. And then once I have that model trained, I can then use it to generate a series of predictions. So that's a simple array where I then take my model, and that should be model, that shouldn't be LM. Okay, good. Yeah, model, predict, and then I take, in this case, my test features, and I get a series of predictions with it. So then we're going to look at score. And this is what we did for project 1. So I'm importing my metrics. In this case, I'm going to look at both mean squared error. I'm going to also look at my R2 score for that. And again, just kind of a simple thing here. For MSE, I'm going to just call the mean squared error method. Very easy to do it y test versus prediction. So remember, all we're doing here is we're comparing our actual test labels versus the set of predictions that we've generated. I'm going to do, and then for RMSE, I'm just taking the root of that. And again, that's sort of a similar metric to MSE, but I'm just taking the root of it. And then finally, I'm pulling up the R squared. And again, same deal. And then I'm just outputting those and printing them. So that's prediction in a prediction exercise in a nutshell. That's what you did in project 1 in a nutshell. So, hopefully in the mad dash to get your code done, this kind of gives you, I guess, a little bit more context of what we were trying to do and why we were doing it. So I guess let me pause there, see if there are any questions about that, about project 1, about just generally kind of how this works and why.
Are those MSE and RMSE and R2 values like decimals because of the data, or is it like actually just a decimal? Because like in project 1, I had like a giant number that was in the thousands.
Yeah, so in R2, I believe in R2 will always be in decimal form. I think that's because I think it's a 0 to 1. R2 is an overall measure of predictive strength of your feature. So it's saying like how much of the variance in the label is captured by the model that you've essentially produced. And so in this case, it's saying roughly 60% of the variance you were capturing as part of your model. So not particularly great. MSE and RMSE, those can be like actual values. Those are just sort of measuring the magnitude of the error. So in this case, I guess the price is, because you're looking at a price, so you're looking at roughly a 30-cent average error for these things. So given that the cost of an avocado, I could pull a describe and seeing it, but I'm just eyeballing it. The average price is hovering around $1, and I'm making and I'm off by 30 cents. That's not great from a model perspective, right? And so that gets back to like interpreting your errors. So yeah, here we're not seeing errors in the hundreds, but when you actually look at the magnitude of the error, that's actually not particularly great output. So this model is, we have not done particularly a good job in terms of predicting the price of our avocados. So any other questions?
Yeah, I have a question.
Mhm.
About the unnamed column. Is that just the indexing number that you just left there?
Yeah,
So-
that's my index number. So
Okay.
from a purely, from a good data kind of cleaning thing, that should probably be dropped from my pipelining thing. I mean, I don't think it necessarily hurts you to have it, but at the same time, it's an indexing column, and that shouldn't be included. So when you're pipelining, just don't include that as part of your numeric features. But yeah, great question. Okay, anything else? So now let me pop over to my slides. Do I have anything? Oh, okay. So let me, we're talking about, okay. Let's, before we get into classification, let's do just a quick kind of check on this. So this is just kind of as a general rule for what steps you should be taking when you're working, with your data. So as you saw before, kind of step one, copy your labels over to new array and then drop them from your data frame. We already talked about why. Then you can drop all features you aren't going to be using. And then I mentioned here, only if not pipelining. And the reason I mentioned that is because pipelining has this nice feature that it's an opt-in rather than an opt-out thing. So if you remember with a pipeline, where's my pipeline thing here? So I define, my right, everything is, it's like the instructions and then what I apply it to. So my numeric features, my categorical features, and this is what I do to each. And the result of that is if I just simply don't want to include certain features, I just don't include them in my numeric features, right? It's an opt-in thing for that. So that's why I mentioned that, like, if you're not planning on using a thing, just make sure it's not part of what you end up pipelining. When we talk about pipelining or fixing the rest and, some things you can do, we've sort of already talked about these. Make sure data is in the type that you want it to be. Have an imputation strategy if you're dealing with null values. For categoricals, you have to kind of choose some form of converting them to numeric if they're not already in a numeric form, and then you have to decide whether or not you're one-hot encoding them. And then for numeric, you may also decide whether or not you want to scale. Split your data, train your data, test it, score it. Okay, so one quick thing to note, well, not one quick thing to note, but there are sometimes reasons why you would do things differently. And one quick example of this is you may want to split your data prior to pipelining it. And the reason for this is something that we're going to call a stratified shuffle split. So here's this really, really cool concept. Till now, every time we split our data, we used, where did we go with it? Train, test, split. This is our basic, raw, kind of stupid, randomized splitter. It says, let's take our data, let's shuffle it into two piles, one that's got 80%, one that's got 20%, and that's my data. Now, there are problems with doing that. And you can imagine that, right? You are kind of relying on a randomizer to split your data. And as a result, it may not split it in a way that is kind of proportionate. And in fact, if you want to do this, this is kind of an easy exercise you can do. If you rerun your model and you don't put a random seed, like right now, I don't have a random seed here. What will end up happening is that it will split your data differently every time. And then if you run your model, chances are you will get different results as a result, because the data that it feeds into the training data that it feeds into your model will be different. So it'll converge on a different thing. So your model will end up being sort of highly reliant on the data that it's given. So, it's fine as an initial method. It's fine as kind of a brute force method, but you may not want to do it. And there are certain strategies you may take to do otherwise. So the first thing to note here is this thing, the stratified shuffle split. This is the idea that says, let's say you know that there's a particular feature that you want to make sure when you split your data, it's being split in a proportional manner, in a representative manner. And so you want to make sure that you're getting a good sampling for it. And so this was actually an example from the sample housing data, the California housing data. So if you recall, in that data, we had created this category, this income category, that we took the housing cost, which was a numeric thing, and we bucketed it. We made 5 discrete categorical things. And so from like a 0 to 4. And then we bucketed and we said, okay, well, bottom 20%, 20 to 40, 40, 60, 80, 100. We bucketed all of our data. And so we got these categorical things. And then what something like this says, it says, okay, while you're randomly splitting, make sure you're getting a representative sample of each in both your training and your testing data. So, and that's particularly important when you're dealing with like features that will have values that will have only like a few values. So let's say for this one, the top 20% in terms of pricing may only have, a handful of things, but you want to make sure that those are showing up in both of your models. And so let's talk about like what that means in terms of, so like for Airbnb, can you guys think of an example of maybe something that you would, for the Airbnb data, something you may have wanted to stratify?
Maybe in the neighborhoods they're a part
Yeah,
of.
Michael, perfect. Exactly right. So if you remember, we had those 5 neighborhood groups, right? That the boroughs, Brooklyn, Queens, Bronx, Manhattan, Staten Island. So if your model, if you just do a train test split, chances are, you might get a disproportionate number of Brooklyn and Manhattan things, but you may not get any Staten Island properties. And of course, that's going to completely sort of change the nature of the model that you're going to produce. So you may want to say, hey, I want to make sure all 5 boroughs are represented in the data that I use to do that. So yeah, so that's a great example for that. Okay, so Sammy, you have a question in the chat about certain parameters. So your first question is about like shuffling and stratifying. So I will be honest with you. I know, so shuffle is actually an important thing. Shuffle says that you take the data and you essentially, prior to splitting it, you literally will like mix it up. And that can be very important when you're looking at data that's collected sequentially, because you may not want to have it that like maybe the first 70% of your data, which is your oldest data, goes in your training, and then the bottom 30%, which is your newest data, goes into testing, right? So you may say, well, maybe there's a hierarchy to how your data was collected, but you want to make sure that when it's divvied up at random. And so shuffling it kind of just adds that extra step to ensure that randomizer is in the case. Now, stratifying, I have to be honest, I'm not sure what if you have stratify equaling yes, what that does. I'd have to read the documentation for that. So I'm sorry, I don't actually know what that does, but at least that's what shuffling does. So yeah, in general, shuffling is a good state to do. So then there's a question about n splits. Yeah, so n splits is, yeah, so n splits is the number of, let me think about in this case what it's doing. I'm actually not sure what that parameter does either. Because you're already telling it to split according to housing, to income category there. So I'm not sure if it's saying within that just to make sure it's representative once or not. I'm honestly not sure. That's something else we have to look up. But yeah, good question. I'll be honest, I'm not familiar fully with the documentation for that. Yeah, so actually, Tommy, I think in the chat, maybe you're right that stratified shuffle, so I could allow you to do this on multiple features. So like right now we're just doing this on income category, but maybe you're going to want to say, you know what, I want to look at not only income, but I want to look at region too. I want to make sure that this is fully represented for that. So maybe that allows you to do it from multiple features. Possible. I'm not sure though, but that could be what that feature is doing. So yeah, if somebody wants to look that up in the background and let me know, you could do that. Oh, okay. Sorry. Doc is saying number of reshufflings. Okay, cool. Okay. So, all right. Sorry. Then I take that back. Yeah. So it's basically, it's how many times you're doing it. So again, this is kind of that added that added sort of randomizer to your data. So it's saying, how many times are you going to do the splitting and the shuffling step? So I guess in this case, we're only doing it once. And just the idea there being that like maybe the more often you do it, the more chances you are that you're going to kind of stir up the pot and get something statistically randomized, I guess. So, but yeah, thank you for looking that up. So then let me kind of pause and then ask you guys something. Now, I just gave you a good reason why you would split your data before you would pipeline it. So that kind of makes sense. So then let me ask you guys another question. Why not always split your data first? I mean, that's a pretty compelling argument for why you potentially want to split your data. So why wouldn't you just always split it first, use some kind of stratification method, and then pipeline it?
Can you repeat why you would want to split first?
Yeah, so you split first. So that's the whole stratified shuffle split. So yeah, so the logic there is, let's say I end up one hot encoding income category. Then effectively what I've done is I've kind of eliminated that as something that you could then use to stratify shuffle split. So the idea being I need to maintain that categorical in order to then do this stratified shuffle. So that's the thought there.
What do you mean by maintaining the categorical?
Sure. So okay, so let me use the Airbnb neighborhood thing as an example. So we have our neighborhood groups feature, right? That had those 5 neighborhoods. So if I one hot encode those, I basically eliminate neighborhood group as a feature, and then I create those 5 binary columns, right? I create a Manhattan column, a Bronx, a Brooklyn, all those sort of discrete columns, and then it's like a 1 or a 0 for them. If I sort of have done that, if I've one hot encoded that, then I don't have that sort of neighborhood group thing that I can then say, oh, you know, when you're splitting your data, make sure each of these are represented. So I would need to kind of maintain that feature in order to do that. Does that make sense?
Yeah.
Okay. Awesome.
So you split before you went hot encode.
Yes, exactly. In that instance, you'd want to split before you went hot encoded. Exactly. So, so let's talk about the other way. So why not always just split first? And here we get into the notion of dimensionality mismatch. So one hot encoding, this kind of devil in the details, is that it will evaluate your data naively, i.e. it doesn't have any prior knowledge of what all the possible values are for a particular feature. It'll just it'll just do a unique, it'll sort of look at it'll do a unique count of all of them. It'll say, okay, well, what are all the unique values? Let me just kind of plug those out and create a feature for each. And so if you have split your data first, there is a chance that certain features will simply not show up in your training or your testing. Particularly if you have features like in our little avocado example, where we have like something on the order of 50 to 60 features, chances are there are going to be certain features that will show up just in training, but won't show up in testing, or vice versa. And so if I then one hot encode them separately, there's a good chance that I'll get a dimensionality mismatch. There's a good chance that rather than getting 66 columns in both training and testing, I'll get, let's say, 65 here, and I'll get, let's say, 56 here. So that's obviously not great. And so that's kind of a reason why potentially you would want to one hot encode your entire data frame prior to splitting it, so that you make sure that features that are one hot encoded you're getting the same number of discrete binary features associated with those values. All of which is to say that my little instruction thing here is highly dependent on the particulars of your data and understanding kind of what you want to do with your data and understanding sort of how to do it. There isn't necessarily a right or wrong thing, and you may at some point want to split first. You may at some point want to one pipeline first. It all really depends on what you're trying to do with the data.
Didn't you
okay,
always
so
have those dimensionality errors though? Because like in the neighborhoods case, like it's also possible to have those dimensionality errors, right?
yeah, yes, it is. So what you would have, well, so there you wouldn't necessarily get a dimensionality issue there because specifically on, so you might get it, but you wouldn't necessarily get it specifically for neighborhoods. And the reason you wouldn't get it for neighborhoods is because what you've told the whole idea is you've told it like make sure both testing and training have all of those feature values included and have them included at a sort of a comparable proportion. So there may be other categories where you'll then get that dimensionality mismatch and you're going to have to correct for that. But at least you wouldn't have that specifically on the feature you were doing the stratified split on. So yeah.
I'm sorry, as a follow-up to that, so the feature that you're doing the actual stratified split on isn't the one that would never result in a dimensionality mismatch. It's because of other features that it could screw it up. Is that what you're saying?
Sorry. Right as I stick a big piece of food in my mouth.
Oh, no worries.
I'm not going to say never, because you can envision a scenario where there's, for instance, you have only one row that has a particular value. And so in that instance, there's simply no way, even if you're doing a stratified split on it, it has to go into either your training or your testing, right? There's just simply no way for it to do otherwise. So I won't say never, but assuming that that edge case doesn't occur, it will ensure that at least for that feature, it's proportional and that all those values are represented in both. Now, again, that'll only be for that value though. If you're dealing with half a dozen categoricals and you're only doing a stratified split on one, chances are one of those other ones will have a dimensionality mismatch. And so at that point, you do potentially have to correct for that.
So if you're trying to deal with something like that, would you potentially want to do like one hot encoding on those other features first, and then go ahead and do your stratified shuffle split on the other feature that you haven't done one hot encoding on? Like, would it be okay to do it like that, or?
Yes. So there are multiple kind of approaches that you could take. So there are several things you could do. The first is you could do precisely that. You could one hot encode those features. You could drop the stratified feature first, one hot encode the others, append it back, and then do it and then split that way. Right. So you could potentially do it that way. Another thing you could do is just opt not to one hot encode those. If you are going to one hot encode those, you could also do value counts for all of those features to make sure that for your other things, you have all of those features things. So you could do a count thing for each and it'll tell you if both your training and testing have them. So, there are kind of checks that you could do or things that you could do to make sure that that doesn't arise. But yeah, one option would be you selectively one hot encode some of your features, append the one you want to stratify on, split it, and then one hot encode that other one. So you could do it piecemeal as well.
Cool, thanks.
Yeah, it gets messy, man. You think this would be simple, but it is not. Oh, okay. Let me go back to the code. But yeah, great question, great discussions. So any other questions, I guess, specifically on that? Okay, cool. So let me kind of pivot over to now. This is going to be sort of a tease for project 2, because I mentioned now we're going to look at a classification exercise. So same data set, only this time we're going to look at, so I have it here. So you can see here, you call a unique function and it'll give you the distinct values within that feature. So in this case, type, I'm going to call the unique thing and it'll give you conventional organic. So those are our two types of things we're going to want to do a classifier model on. So now our new feature is going to be this. Our feature, now we're going to do a new X. This case, instead, we're going to leave the price in it. And we're going to just drop date, which again, we're not using, and we're going to drop type because that's our new set of labels. We're going to again pipeline it Nothing has really changed there. One additional step though, because remember, we said we wanted, now our labels are in object form. We have conventional and organic. So we need to do something with our labels. And there is this really, really useful thing called a label encoder. And that will simply, that's one thing you could do. You could do a as type int as well. You can convert it to an int that way. But label encoder will just simply kind of take your array and will convert it into sort of a set of numeric values. So in this case, now I've converted my conventional organics into an array of zeros and ones. And an important thing there, because your label is a single dimensional feature, it's okay if you have multiple values there, because that's precisely what you're trying to predict. Now you can also, if you want to, you can kind of also manually assign things if you want it sort of ordinal. But if you don't really care, you just want a label assigned with it, which is what we do. Label encoder is a nice, easy, quick method to do it. So again, just like with the classification, we're going to do our train test split. Nothing's changed there. You're going to see also very little has changed in terms of your actual model and your metrics. So in this case, we're going to import something called a logistic regression. I don't think that's been covered yet in lecture. We're going to cover that, but that's going to be one of the classifiers that you're going to use for project 2. I'm going to import it. The process will be exactly the same as when you were doing a predictive model. So in this case, I'm going to get a specific instance of it. I'm going to fit this to this. I'm going to generate my set of predictions using that model that I've trained. I'm going to get a, okay, so this score, do I need? I don't think you actually, sorry. Ignore that line. You don't actually need that for the sake of this. You would need that for something else, but we're not going to deal with that for this exercise. That's going to be for your ROC curve, which we'll cover next week. And then the final thing is your metric. Your metric is different. Before we were looking at things like mean squared error, root mean squared error, R squared values, things like that. Here, we're looking at something called accuracy, which is just simply the percentage of predictions that you get right. And you've imported your metrics, so you can just call accuracy score. Just like the other things, you just compare your predicted array versus your actual array. And in this case, I have an accuracy of 97%. So that is pretty awesome. And perhaps unsurprising, given that I have features like average price, unsurprisingly, conventional versus organic, I would imagine are highly associated with things like price. So as you can see, it's the model is basically, the process is pretty much exactly the same. The only things that really change are the precise metric that you're going to call and the different model that you're going to import. But in terms of your process flow to do a classification exercise is pretty much identical. So most of the code that you used for project 1 is going to carry over into project 2. Let me pause there and see if you guys have any questions specifically on sort of doing a classification.
I think I might have missed it, but with the label encoder, did we only have 2 different like classifications that we go by? That's why it's 0 and 1.
Yeah. So generally, if you're doing a binary classifier, it'll be zeros and ones. It doesn't have to be. I mean, it could be 1 and 2, 2 and 3. I think those numbers are arbitrary, but generally speaking, that's usually how we do it is in terms of zeros and ones. And the label encoder will just assign, based on the number of unique values, it'll assign a number for each of those unique values starting at 0. So yeah, good question. Okay. All right. Let me pause here. Actually, before we dive, so here's, oh yeah, good question. So why is one hot encoding bad in that case? One hot encoding is bad because those are your labels. So your label will always be a single dimensional output. That's the thing that you're trying to predict. So you're not going to predict multiple dimensional arrays. You have that one single thing about it. It's like your X's and your Y. That is your Y value. Okay. Okay, so Daniel, there's a question about removing outliers. But yeah, do you mind if we push that to the end of discussion?
Yeah, no, that's what I said. I was like,
Okay.
only if there's time, just save it for the end.
Perfect. Okay, perfect. Yeah. So then there's a question on what if we have multiple? What if we're doing with a multi-class classifier? So the short answer is it would still be a single array. You would still have that single kind of thing, but your model would have to work a little differently. And we can get a little bit into that as well, because there are some classifier models that will actually work well for multiple classes. There are others that you need to do a little bit of kind of massaging of it. So for instance, there are different techniques you could do, which is one is called like a one OV, I think it's OVA, one versus all. And so this is just like an example of how you would deal with a multi-class classifier. If your classifier model can only handle a binary classifier, there you take multiple classifiers and you just do one versus everything else. So if you're dealing with three labels, you would do label 1 versus everything else, label 2 versus everything else, and label 3 versus everything else. And then you would just return whichever one happened to have the highest probability associated with it. So, so you can handle a multi-class classifier with that. But yeah, regardless, it's all going to still be one feature. Your labels will still be one feature. Okay. So, okay, before we dive in, can somebody, before I forget, can somebody in the chat tell me who ended up winning the pajama contest? Or not necessarily in the chat, but can like somebody tell me who actually won? Isabel. Oh, wait a second. Why is my screen acting on? Okay, Isabel, you got to take a victory lap. You don't have to like literally take a lap, but
Yeah, we're in a cramped apartment. Also, Tammy's here. In the same discussion. How cute of us. So I'll just do a little.
Well, congratulations, Isabel. Can you send me your preferred email?
I'll private. Yeah.
Okay, because you got Starbucks inbound. Awesome, awesome job. Okay. Well, woo, everybody. Where's the hands up? I'm doing the clapping emoji. Yeah. Okay. All right, so for the rest of discussion, I wanted to talk a little bit more about homework 1, specifically some of the intuition around some of the problems, kind of work through, I guess, an example with you all, introduce some of the key themes of project 2, and then depending if we have time, which I don't think we have, I have some also slides around KNNs. I don't think we're going to get into that because I've already given you a lot, but who knows? We'll see. It depends if we're ambitious. Let me share the screen again. All right. So some of these things are going to be sort of questions. I assume, I hope you guys have started project homework 1. If you haven't, these are just kind of some things to think about. So like for your first question, when we think about like some problems with your data collection, and the thing that I want you as a burgeoning data scientist to think about is just the fact that we have a natural bias when it comes to looking at numeric data, right? You have a spreadsheet full of numbers and you have just this intuitive sense that, oh, this is accurate because numbers never lie. And right, there's this kind of sense that, oh, the data you're been given is intrinsically accurate. And that's obviously wrong, right? Data is the product of humans that collect it, and that's subject to all manner of biases, inaccuracies, inconsistencies. And so part of your job as a data scientist is both when it comes to experimental generation, when it comes to coming up with data collection exercises, as well as when you're given a data set, is understanding maybe some of those intrinsic biases and understanding where some of those inaccuracies might be. Because ultimately, your data will only be as good as your model will only be as good as the data that you feed it. So if you are not kind of thinking through some of these errors or some of these things that kind of can bias your data up front, then that's going to kind of just cripple everything that comes following. And I think that's kind of a really, really important thing to bear in mind, because I think a lot of, particularly people who come at this from, people come to data science from all sorts of disciplines, but I think the problem is particularly for people like us who come from STEM backgrounds, we naturally kind of take the data and like, for us, the interesting things are the model. That's the interesting thing is like, all the coding side of it that comes afterwards. And, it's just let's just load the CSV file and just get to work. Right. Whereas if you, whereas if you are like doing something, if you're coming at this from like, let's say a sociology or some other sort of thing that's more, I guess, externally focused, you may just have a natural inclination to say, okay, what are the biases in the data collection? What are the issues or challenges of that? So thinking about that, thinking about those problems, thinking about those things is kind of an important, I guess, instinct for you as a data scientist to develop. And that's really what we're looking for with question one in particular, is to say, okay, well, this person comes to you, they have sort of a thing, where might some errors be? Where might some errors be in terms of the sampling? Where might some errors be in terms of the kind of sentiments you're going to be gathering? Things of that nature, I think, are kind of important to bear in mind. So, and then sort of the next, I think, challenge that a lot of people have, well, not a lot of people, but a lot that you will have as a data scientist, is there's kind of an implicit translational step when it comes to sort of taking problems that are sort of abstract and turning them into concrete data science specific problems. And so in that case, like, you're given a prompt, you're saying, use a predictive model for a student that will do well in a class. And that's the kind of thing that, like, on a intuitive sense, you sort of say, okay, well, I intuitively know what it means to do well in a course versus not. But translating that into an actual kind of numeric or quantifiable thing is oftentimes quite challenging. And I sort of, there's a Piazza post about it where we talk about that a little bit more. But it's like, it's how you approach that problem can vary dramatically. You may say, okay, well, this is a categorical problem. This is a students who do well, students who do not do well. And if you're looking at a categorical, well, how do you draw the line? Are you looking at percentiles in the class? Are you looking at grades? Are you looking at this? Where do you kind of draw your line for that? Or is this a predictive model? Do you want to sort of build a model where you try to predict either their numeric grade or their letter grade or something like that, right? There isn't a right or a wrong answer to that. And part of your job as a data scientist is understanding how to frame the question in a way that makes most sense. And I can tell you, like, that's not an intuitive process. Like, we did a final project back when this was CS148. We did a project with a corporate sponsor, and the challenge we had there was we were trying to generate a label about, it was with a trucking company, and we were trying to generate a label about, like, we were trying to predict what truckers in their fleet would be sort of the high performing ones. And it turned out that was a very non-intuitive thing about, like, what actually constituted drivers. And I can tell you right now, we ended up not actually using a particularly good definition of that. And that kind of crimped us. So we had to kind of rush that out. So we went with a definition of what we thought high performing drivers would look like. And then we started playing around with the data and we realized we had actually sort of missed some important things. And, you know, looking back, we realized we actually should have done our labels completely differently. So again, it's thinking about taking what is inherently sort of a abstract conceptual idea and translating it into something that is a concrete model that you can train, you can get outputs and make sure that those are meaningful. It is sort of a non-intuitive thing. And then the final step, and we've been playing around with this, but I think it's important for us to kind of take a step back because we spend a lot of time talking about like one-hot encoding and things like that, but I don't think we've ever kind of taken the step to say like, why are we doing this? Or what is this actually helping us with? And this is kind of the third thing that like as a data scientist is particularly challenging. And that's really answering the question of like, am I modeling the relationship between features and labels correctly? And, you know, so you have here this, you know, y equals mx plus b, right? And we've sort of talked about that from the perspective of a linear regression, where essentially what we are learning here, and I know, you know, professors spent a lot of time in this in class and sort of interpreting the m and the b and like understanding what each of these coefficients mean and how, you know, a change in this feature value corresponds to sort of this change in your overall label. And we sort of intuitively know that relationship can be there, but oftentimes that relationship is much messier, is a lot messier. And part of your job as a data scientist is to figure out, you know, am I setting up that relationship properly? Am I setting up in a way that kind of accurately reflects the dynamic between X and Y? You know, is this nice, simple, ordinal relationship where a value change in X will have this corresponding sort of weighted change in Y? Or is maybe the relationship a little bit more complicated? And let me give you, and I think it was kind of helpful for us as a class to kind of just walk through sort of an example of this at a theoretical level, because again, I don't think this is something that we do in this course. And I think it's helpful just to maybe give you guys a little bit more of an intuition of this. Okay, so I told you this was going to be an LA themed class, and indeed it is. We're going to talk about LA traffic, a subject near and dear to our hearts. Classic machine learning problem. Predict drive time, right? You hop on Google Maps, you plug in UCLA's campus, you want to be on time for your discussion section, and it is telling you it's going to be a 50-minute drive. Oh no, indeed, that is not what we are looking for. Okay, so classic ML problem. Let's think about sort of 3 example features, and let's think about how we as data scientists could model those features in relation to our goal. So these 3 features are locations. Let's say you're looking at data, you have the location of the car, and you have that in terms of longitude, latitude, you have time. You have a numeric, you know, this is sort of a numeric feature of time. And maybe it's in some form that we've talked about before, maybe it's just in thing, but you have some kind of indication of time. And then the final thing is you have directionality. So categorical, north, south, east, west, right? All of those, if you were trying to build a model to predict drive time, you would say all of those features are probably important to doing that. Right? I mean, there are other things that are probably also important for a model, but at least for our sake, these 3 features are probably deeply, deeply important. And so, you know, intuitively, these all seem useful, but the relationship between them is a bit messier and is a bit nonlinear. And let's kind of talk about that. And let's talk about why I can't just take these 3 features as they are, plug them into a linear regression, get a prediction, right? I mean, you could do that, but chances are you're not really, again, you know, if you think about kind of going back here, if you think about this relationship, you're not actually kind of plotting that relationship properly. And okay, where is the thing? And let's kind of talk a little bit why that is. So let's start with location. So traffic trends will never, almost never, uniformly kind of shift over a directional axis. So remember, we have longitude and we have latitude. So it will almost never be the case, if you're thinking about like a map of traffic, that you will get this nice clear relationship between as you're moving along one axis and traffic, right? Instead, they will cluster, and you will see sort of around sort of key neighborhoods, around sort of key areas, key sort of traffic intersections. That'll do it. So you may see, as you're sort of thinking about like looking at a map of LA, right? As you approach downtown, as you approach Santa Monica, as you approach certain sort of critical highways, the 101, the 405, the 10, right? As you approach those kind of choke points or those sort of target destinations, traffic will naturally go up. But as you continue going, it'll go down and up. So like if you were plotting, if you were looking just, for instance, at one of those axes, you might see a plot that looks like it goes up and then down and then up and down and up and down. And so there isn't this nice, clean kind of numeric relationship, right? Again, going back to this, y equals mx plus c, you don't have that sort of clean thing where you can just plug in a latitude and get this thing and just expect sort of a nice linear relationship between them. Location just doesn't work that way. Time, we have kind of a similar thing. There will be natural sort of peaks and ebbs over the course of the day. You will have times where, around rush hour, where traffic will go up, and then suddenly you'll be passed and traffic will go down. So again, I don't have that nice kind of capacity to build that relationship with it. And then, direction, direction is obviously very important, but it's also very time sensitive. And if you think about like rush hour, rush hour is typically very directional. So, in the morning, traffic into a city center will be very high, but traffic out of it will be almost non-existent. And then conversely, in the evening, traffic out of the city will be very high, but traffic into it will be almost non-existent. So directionality is clearly important, but it's also very time sensitive. So again, if I'm thinking about this relationship here, I can't just have a uniform, westbound will have this nice coefficient, because westbound will really matter on the time of the day. So all of which is to say, these three things, I have them, they're numeric, I can plug them into my data frame, I can run a linear regression, but am I actually plotting that relationship? And clearly the answer is no. And so if I get a model, chances are I'm not actually generating anything that's of real value, even though I have data that clearly is valuable. So there's that added step that you as a data scientist have to do to engineer your data to set up that relationship more properly. And again, I don't think that this is something that's kind of explicitly explained in the course of the lecture. And so that's why I kind of want to walk through this, because I think that's something that we don't really talk about. So let's talk about some things that you could do to maybe help. So the first thing we can look at is blocking. So blocking continuous variables into discrete categories. So here, this is kind of a very useful exercise that we can do for this is with location. So we know, as we said before, it's not really useful to look at like longitude and latitude as a numeric thing, but we understand that there are certain neighborhoods, certain zones, certain areas that we can expect traffic density to be heavily impacted. And so part of what you may want to do from a feature engineering, from an augmentation standpoint, is to take those longitudinal and latitudinal values and essentially try to create sort of a series of categorical chunks, if you will, blocks, right? So we can see something like a neighborhood as an example. Say, okay, well, let me kind of grid off downtown. Let me grid off Westwood, Brentwood, let me grid off these certain areas and then create categoricals and then assign weights associated with those. So that might be a much more useful indicator to feed into my model than just that raw latitude, longitude thing. And same thing may be the case with time, right? It may be a lot more useful for us to think about time in terms of these discrete chunks, in terms of morning, afternoon, evening, than it'll be to have it as this kind of continuous variable, because morning rush hour will look very different than afternoon or evening. Another thing, and this is something that we explicitly talk about with one-hot encoding, is we can do what are known as cross terms. And the idea here says when we have features that are essentially co-related, that it's not really useful to look at them independently, we can sort of create a series of discrete sort of independent values, and we can model those values independently. And that's a cross term. So in this case, we're saying, you know what, let me look at the cross term between direction and time, create a feature specifically for each of those permutations, and then let's model that relationship specifically. So in this case, we can look at heading east versus morning, heading north versus evening, things like that. But the idea there being, when we say, you know, directionality is so tied to time, let's take each of those specific things and let's model that relationship. When we're building that, you know, when we're solving for M, let's say, okay, well, let me look at what westbound in the evening looks like. Let me look at what eastbound in the morning looks like. So that's a cross term that we can try to do. Another thing that I'm going to mention here, that's kind of an interesting approach that you can take as a data scientist, is you don't necessarily have to build one model either. So there's this notion here called period regressions that says, you know what if I look at my data and I say, you know, my data is so seasonal, my data is so dependent on different things that effectively the difference between morning and night is so dramatic that it really doesn't make sense for me to use a single model to predict traffic the entire day. I should instead figure out, you know, those periods where traffic is consistent within the period, but not across periods. And let me build a model specifically for that period. So let me do a regression for morning rush hour. Let me do one for, you know, evening rush hour, and let me do one for off hours, just as an example. So rather than trying to build this one single equation that will capture the entirety of traffic in LA in a 24-hour period, let me think about maybe modeling for particular areas, or maybe modeling for particular times. So that's the idea of a period regression as well. You don't need a one model fits all. And again, this is just kind of a partial thing. This isn't an exhaustive exploration, but it's an idea of beginning to think about how you can engineer your features to better reflect this relationship between feature and label. And rather than just saying, oh, it's numeric, great, plug it into the model, but saying, actually, here are some things that I can do to better reflect that relationship between them. And remember, you're not necessarily inventing new information, but you're simply reparameterizing or reframing your information in a way that more closely aligns with what you're trying to do. Okay, let me pause there because I do want to talk then about one-hot encoding now that we've had that frame, but let me just ask if there are any questions specifically about what we just covered. Okay, so clarify the information, no problem. Yeah, exactly. So in the chat, Neil, that's exactly right. It's you know, there's problematic on a superficial level of, is this numeric versus non-numeric, but it's the idea of precisely saying, just thinking about that relationship and saying, is, you know, am I accurately mapping the relationship between my feature and my label? And so, you know, again, using the location as an example, yes, I could just fit latitude in and I might be able to get a coefficient associated with it. But is that actually kind of the same idea? So yeah, good question. Okay, so Chelsea, there's a question about kernelizing a variable. So I know the term kernelizing in another frame of reference. I'm not sure what you're asking in this term. Would you mind clarifying that?
Yeah, like in machine learning, they taught us about kernelizing, where you map your variable onto like another, I guess, space. And I wonder if this is like a similar idea or is like totally different.
Yeah, no, it's different, but okay. So let me. So remember earlier when we were talking about how if you increase the dimensionality of your features, even if you don't add any more information, it makes it easier to sort of get like to get your model to split cleanly just because you've made your data effectively sparser and more spread out.
Yeah.
So that's the idea of a kerneling thing. And so it's one of the tricks that you can employ if your model is having trouble kind of getting clean separation. One of the tricks to actually achieve that is to do precise that, is to take your existing data and cast it into a higher dimensional space. And when you do that, you can actually then kind of get your model to cleanly separate your data.
Okay.
So yeah, so it's kind of a different approach, but yeah, I mean, fundamentally, it's about taking your existing data, right? In both of these instances, you're not creating new information. I think that's kind of the key thing here. You're not inventing new information. You're taking the existing data. You're just doing something different to it to make it more useful for your model. So in kerneling, it's about achieving a cleaner kind of separation in terms of your classifier. Here, it's about better representing that relationship between features and labels and how those two are interrelated. So, but yeah, great question. Okay, so I want to use the introduction we just had, all that kind of conversation around sort of engineering your features to say, okay, well then let's talk a bit more about one-hot encoding. Because I think when we introduced the concept, we really talked about what it avoided. I.e., if you have a categorical feature that has multiple values and we didn't, we need to assign numbers, right? That was the sort of the crux of our dilemma is we have to convert it to a numeric, but we didn't want to introduce an artificial hierarchy. If you have, let's say, a category of fast food joints, so you've got your McDonald's, Burger King, Wendy's, In-N-Out, whatever, like you have all of those. You don't want to, I mean, maybe you do, but like assuming you want to effectively treat them equal, you don't want to put a hierarchy to that thing. You don't want to kind of just assign numbers that then your model will assume there's that ordinal relationship where there isn't. So we talked about saying, okay, well, one-hot encoding is a way of avoiding that. But I don't think we've really talked about what you're achieving when you one-hot encode. And so this is kind of what I want to get at with this. When you have a category of functionally independent values, each of which you think will have an impact on your label when it's present. So there is a relationship between that particular value and your label. One-hot encoding allows you to capture and model that distinct impact. That's kind of the key thing that we're doing here. So, an example I have here is fashion. Let's say you take fashion brand and you're trying to model clothing price. So each label will clearly have a multiplier effect on the product price, right? I don't need to expound on that. H&M will clearly have a different impact on price than a Gucci or a Prada, right? Clearly. However, it's not always sort of a direct linear relationship, but you still want to capture that. You want to capture what multiplier effect an H&M will have versus a Gap versus a Banana Republic. So allowing you to one-hot encode basically allows you to isolate each of those sort of distinct values and allows you to train a coefficient specifically with that. So your y equals mx plus b, you essentially, by doing the one-hot encoding, you get to do coefficients specifically to those specific values. And I think that's what's so kind of cool and so powerful about that as a tool. Again, it's not something that there are downsides to it, which we've kind of covered, I think, at length at this point. But one of the things that make it so powerful is precisely, it says, like, in those instances where you have clear relationships between features, but they're not, they're not sort of in an ordinal matter, right? It's not the case that you can just say, even if there's varying degrees of multiplier, you can't necessarily stick in a nice thing where you say, Louis Vuitton is 1 and Chanel is 2 and Dolce is 3, right? You can't, you don't have that nice little linear thing where you have that singular coefficient thing, but you understand that each of those values have an associated multiplier. One-hot encoding allows you to capture that in your data and reflect that in your data. And again, cross-term allows us to do that too. It allows us to say, okay, when we know that there is a certain combination of features that maybe when they are by themselves, we're not capturing that relationship, but when we have them in concert with each other, again, direction and time being, I think, a good example of that intuition, going westbound on the 405, no, 405 is north-south, going westbound on the 10 during, evening rush hour is going to be a very different experience than going eastbound on the 10 during afternoon rush hour, right? So it's the idea of saying this is clearly there, but I want to isolate that specific interaction because I understand that it's in concert when those occur. So that's really what you're doing when you're one-hot encoding. And I think that's what makes it so valuable and so powerful as a tool. So it's a lot more than just kind of breaking down the artificial hierarchy. It really kind of gives you the chance to model that specific relationship when you know that it's there. Okay, cool. So, okay, let me pause there. I'm sorry, guys. I know that was a lot, but yeah, so in the chat, there's a question of like, is there a lot of trial and error? So there is a lot of trial and error. So I think, so there's two things I want, kind of two takeaways of this. The first thing is doing data science. If there's kind of one of the key takeaways with this course, doing data science is easy. Doing data science well is hard. And that's going to be kind of a persistent theme with this course. The barrier to entry is very low to do data science. I mean, you have basically already covered 90% of the code you need to do to meaningfully do data science. It's not, it's the kind, you can spend a weekend and you're there. It's doing it well that is where all of these kind of nuances come into play. And I think one of the sort of key takeaways I want from today is the importance of understanding the domain in which you're interacting, right? A lot of how you model that relationship between your data and your labels requires domain expertise, requires that knowledge, that insight of it. And, if you're just plugging in data at random and you're not really understanding that relationship, it's going to impact your output. There's only so much you can do if you just don't kind of have that domain expertise. The other thing, to your point, is that yes, there's a ton of trial and error to this process, and you're going to see that with Project 2. It's you literally, a lot of this is you just trying out different things and you seeing what works. Because yes, you will have an intuition about what things might perform better than others, but a lot of times, we're going to learn a ton of different classification methods. There's really like a very kind of diverse array of ways in which you can computationally classify your data, and very many different approaches. And it works for different types of data, and it works for different types of permutation, different types of things. But until you try it, you really don't necessarily have the kind of the full intuition to know what will work well. And so that the reality is like that really is the process for most data scientists. We have data we'll try to engineer, and then we'll throw like a dozen different models at it, and we'll see what works. So yeah, it's a lot of trial and error, and that's what you're going to see actually in Project 2. Project 2 is we have a data set, and we're going to try a number of different classifiers. And within those classifiers, we're going to try to sort of tune a lot of different parameters and see which one works. And yeah, there's just a ton of stuff to do there. So yeah, great question. Anything else? Okay, so yeah, so the last thing I just kind of wanted to tee up for today's discussion is just an overview of Project 2. I think we've kind of already covered a lot of it incidentally, but so we've already talked about sort of the differences between prediction versus classification, and for if Project 1 was about just getting your hands dirty with the code, this is where you're going to really begin to understand the underlying mechanics of the code. What are you doing and why are you doing it? And our goal here is really going to be to try to create an optimal model for our data set. So we have a particular data set, we have a particular problem. We are going to try a number of different classification techniques, a number of different sort of ways of tuning it, and our goal will be to kind of test those out and see how those impact performance. And Sammy, to your point, it really is a you know, throw the proverbial kitchen sink at your data and see what works. That really is the case more often than not. I did mention this early on with the KNN. We do kind of, just to show you, I guess, the importance of pipelining and how those can really, that's funny, Daniel, you noticed that. Yeah, sorry about that. Yeah, I do have to be a little more quiet. I was waking up a certain somebody. So that's funny that you caught that. But so, you know, so as I mentioned, sort of as a first step, you're going to have KNNs, and I want just to take the exact same data set, one in which you haven't scaled it, and then one which you have, and plug that exact same thing in your model and just see how the performance changes. So, you know, that's going to kind of be an important thing. And then we're going to show you, like, there's a lot of ways in which you can tweak your model. And this is where we're going to start to get in the weeds of like different normalization penalties, different solver models, different gradient descent models that you can kind of be using, and how that's going to impact your performance with that. So we're going to get into that. There's going to be a lot more qualitative questions on this project. So a lot more kind of thinking questions on this, like taking your results and trying to interpret them and understanding what the different performance that you're getting, how that's kind of impacting it. There is, I think, going to be sort of another thing that we're going to spend a lot of time for project 2 is thinking about other measures of success. And we've already talked about this a little bit with project 1. You know, we were talking about how different measures for error matter. And we were talking about how things like MSE, where you square your error term versus taking the absolute value of an error term, how that disproportionately penalizes sort of higher magnitude errors, right? And how a model that focuses on something like MSE kind of prioritizes a lot of low-level small errors within a range, but kind of penalizes anything that diverges too hard. Well, we have kind of the same idea here with classification. There are different types of errors and different types of things that we may want to do it for. So in our coding example, we did accuracy, which is just a simple percentage I get right over, well, it's the number I get right over the total number, right? It's a very simple, very intuitive thing. But we're going to find that there are times and instances where the type of error matters significantly. And, you know, this is just like a funny but intuitive example of that, where you may not want to make certain errors. So first example is a false positive, where you label something as being the case where it's not. And can anybody think of some examples where, you know, we'd be very nervous about false positives to the point where maybe we would overcorrect our model and maybe decrease our overall accuracy, even if it meant avoiding false positives?
Well, you already have facial recognition by police, but I was thinking about maybe like the US court system, where typically in favor of like innocent until proven guilty. So you need like consensus to like put someone for like murder charges. So it's like favoring like a false, or favoring against a false positive.
Yeah, so Tommy, great example to do it, right? There's the, you know, there's the, in our judicial system, right, there's the presumption of innocence. There's the innocent until you're proven guilty. And not only that, but like when it comes to evidentiary standards, we say that in order to convict somebody of a crime, do you guys know what the standard of evidence is for a criminal case?
Beyond a reasonable doubt.
Yeah, exactly. But not, that's exactly right. Beyond a reasonable doubt. So there are different standards. So for civil cases, well, let me ask you, does anyone know what the evidence is for in a civil case?
I think it's just a majority, something like that.
Correct. Well, so the actual term is a preponderance of evidence. But yeah, so if it's a civil case, if it's two business owners suing each other for damages. In that case, we just simply look at the preponderance of evidence. We say, well, what is the most likely result here? As you said, the majority, as it were. But for an actual criminal case, there is the beyond a reasonable doubt standard of evidence that says if you want to convict somebody of a crime, you have to prove it beyond a reasonable doubt, which is obviously a much higher standard of evidence. So yeah, so I think criminal justice in general is an example where we are very, very concerned about false positives, to the point where, again, as a result, there are a number of criminals where the evidence suggests they did it, but we're okay bringing down the overall accuracy of our judicial system if it means we avoid false positives. So yeah, so that's, I think, a great example of where if you're thinking about that from an ML perspective, you may want to avoid that. Okay, and let's talk about the flip side, false negatives. That's where there is something, it should be labeled as that, but we do not label it as such. Okay, good. So, obviously, I think a lot of people are kind of jumping on about medical diagnostics. So predicting diseases, COVID-19 tests. Yeah, so that's exactly right. Where, right, and there's, I think, an important, I think there's an important kind of distinction there between maybe like a preliminary diagnosis and a full diagnosis. So, for instance, you wouldn't necessarily want to tell somebody definitively they have cancer and they need to get on radiation treatment if they don't, right? You probably would. So you can imagine something where you have like a preliminary diagnosis where you say, okay, well, there, we don't want anything to potentially slip through. If there's even a potential, there's even a chance they have this disease, we want to flag it. But if I'm making a definitive diagnosis, then I don't want them going on chemotherapy if they're not, right? So even there's a little bit of a balance where it's not always the case. So yeah, so I think, again, when we think about classification, this is kind of another thing where like you as the data scientist have to think about what success looks like, and you have to think about what you have to prioritize. And so that's another thing we're going to cover for project 2 is, looking at generating different metrics for how your model performs and thinking about the comparative success or otherwise of why you would go with one or the other. So, okay, I got bonus content where we start digging into KNNs. I'm kind of feeling like I threw a lot at you, but I mean, if you guys want to keep going, we can keep going. If not, I can kind of pause here and just open it up for questions. What do you guys say?
Yeah, I'm good with keep on going.
Okay, I'm hearing one vote to keep going. I'm hearing it look like another person wants to keep going.
I don't mind either way, but I have a question that if that's cool. So
yeah,
I was like looking at the timeline for project 2, and given that we only had like 1 weekend for project 1, does that mean that the fact that we get 2 weeks for project 2 mean that it's that much more difficult, or is it just how the timeline ended up?
Okay, yeah, great question. So it is more difficult than project 1 in that you're not just directly, I mean, once you get the code down, you pretty much are just copying and pasting. It's not that much. I mean, but there is a little bit more work. It's a little less structured than project 1 was. And there's a little bit more theory and concept work. So it is more work. It's not 2 weeks more work. I think the discrepancy between project 1 and project 2 has a lot more to do with project/homework 0 than anything else. Because I think when this class had been taught previously, we hadn't had that initial sort of Python coding exercise. We had just kind of dove in directly with project 1. And the feedback we had gotten at the time was that, there needs to be a little bit more kind of upfront work to get people up to speed on Python. And so we kind of crammed that in, but we didn't really adjust the deadlines for project 1. And I think in hindsight, we should have given you a little bit more time for that. But to your point, it's a little bit more work, but not 2 weeks worth more work.
Cool, thank you.
Yeah, absolutely. Yeah, any other questions on just like, I guess, anything that we covered today or project homework?
I was wondering, was it a lab you were going over at the beginning? I missed the beginning part.
Oh,
so I
yeah.
didn't-
So no, that's not a lab. That is a coding sample I threw up here. So it's on both the website and the thing. I think we threw up the link in the chat as well. But yeah, so you can load that there. Let me know if you can't find it, and I can throw that up again. But yeah, it's also available on my section website here. Okay, so all right, so you guys want to do KNNs? Well, we'll do KNNs. Okay, so this is sort of the first model we covered in class, and I think it's kind of a it's sort of interesting, and it's a little bit different than the other models we're going to cover, in that virtually every other sort of machine learning model we're going to cover, there is this intuitive step that you are building a model, that you're part of the process of sort of constructing the machine learning model is that it takes the data, it learns something about that data to create a model, a sort of a representation of the data, and then it uses it for the purposes of prediction or classification. So intuitively, the classic example, this is linear regression, right? Where we have those coefficients. We're learning the mx plus b. We're learning that m and b. We're learning the coefficient. We're learning your y-intercept, right? We're learning what those are in relationship to the features and labels. KNN is different in that it's lazy, in that you're not learning a model about your data. The model is the data. And I think that's kind of an important distinction between them, where literally, and you'll see that the data becomes your model. If you're looking at just a nearest neighbor thing, your nearest neighbors are is the data set. So the other thing to note about this is that it's non-parametric. It doesn't make any assumptions about the way the data is distributed, how it's scaled, anything like that, and we already kind of went into why that could be problematic. We talked about, if you don't scale your data, how that can impact and throw off a KNN. But there's some pluses to that too, and we'll get into that too. But the reality is, it fundamentally, it takes the data as is. It doesn't make any assumptions. It doesn't learn anything about it. It doesn't try to optimize it. It just says, here's the data I'm given. Here are the nearest neighbors. Here's my output. So how does a KNN model work? In this case, so we have to kind of rethink what it means, like training and testing. Because in this case, again, there's no implicit training step when we work with a KNN. Instead, our training data becomes our model. Fundamentally, the data that we load is our model. And then, the sort of the key parameter for a KNN is K, is the number of neighbors associated with it. So in this case, you define the number of neighbors you're going to be looking at, and then and then sort of the final thing is you sort of load your testing sample. So again, your testing data in this case is the thing you're actually going to sort of look at the performance of this associated thing. So then you load up a point. So in this case, this is a classification example. So in this case, my red dot here is the point I'm trying to generate a predictor for. I count, in this case, I have a K of 5. So I have 1, 2, 3, 4, 5. In this case, my K value, I count the nearest neighbors, and I use it to generate a prediction. And for KNNs, if it's a classification, my prediction is simply, it's a majority vote. It's whatever happens to be the majority class of neighbors. And that's fundamentally how it works. I just load a point. I look at its nearest neighbors, measured again by Euclidean distance. Well, measured by distance. Let me not say Euclidean, because you can actually not use Euclidean. Measure by distance, and then I use that to generate a predictor. So one thing that we've already kind of mentioned, we've mentioned that one. Yeah, okay, so we've mentioned all that, cool. So let's kind of talk about some advantages and disadvantages of this. So the biggest advantage up front is that we can immediately begin classifying once we have that data set. It's literally plug and play. You just load it and you can immediately begin classifying. It can also be fairly good at sort of understanding the data that we're working with, right? If we're dealing with data that tends to cluster, if we have data that is linearly separable, you can get a good understanding of your data using a KNN. And then the other thing to note is that it really works well. A lot of classifiers require linear separability, require that you can sort of segment your data into sort of areas, and KNNs don't. KNNs work very well with data that is nonlinear, that can be multi-classes. It can actually work really well. And again, data sets with different clusters do really well with clustering models like KNN. So an example I have here is type 1 and type 2 diabetes. So does anybody here, can anyone tell me what type 1 and type 2 are? Just at a high level.
It's like genetic, where you don't have the ability to produce insulin, and the other one is like after like using your or like you become resistant to insulin after eating, or your eating habits.
Yeah, Chelsea, that perfect description. So fundamentally, diabetes deals with like insulin resistance, insulin breakdown, where your body, for whatever reason, doesn't produce enough functional insulin where you can sort of process blood sugar properly. So, right. So one type is genetic. So people can be born with that. They have the inability to produce a proper amount of functional insulin, and it's lifestyle independent. It is what it is. You're born that way. Type 2 is generally lifestyle. So if you poor, lifestyle habits, obesity, heart disease, a number of comorbidities over time can lead to sort of a degradation in insulin, can lead to what's known as insulin resistance. So the reason I mention is I think that's a kind of a good intuition for like clustering, where if I'm trying to build a classifier model for diabetes, the types of diabetic patients will look very different, right? One may be very old, maybe very, may have a lot of comorbid diseases. The other may be young, generally healthy, right? And things may look very different, but they'll both have things. You'll have these like clusters. So KNN works really well for that. Other things it doesn't. Some disadvantages, you have to keep the entire training set in memory. So it can be computationally very expensive. For that reason, it doesn't very scale well. And like we said, it doesn't learn your model very well. So generally KNNs as a technique, they work best on smaller data sets that don't have many features and are nonlinear. That's kind of the sweet spot for a KNN. Let's think about what we can do for KNNs. So the first thing and the most obvious thing that we can kind of tune is K neighbors. So the number of neighbors that we have. So, you can have a K equals 1 where you literally just take whatever value happens to be closest, and that's your K. You can take a higher number. And generally speaking, higher numbers of K will tend to smoothen your decision boundaries. So I have an example here. I think this is blocking this. Yeah, where K equals 1 and K equals 5. And so as you can see, what generally tends to happen, right, is as you are kind of aggregating, as you are summarizing, it tends to smoothen your decision boundary. It tends to make a model that generalizes pretty well. But again, you can kind of, there's that balance there. And that's one of the things that we're going to actually have you do in project 2. We're going to say, take a KNN and then test out different values of K and see which one works best. And what you'll find is that there tends to be that sweet spot where you'll find a number that isn't K equals 1, but also isn't K equals 100, where you sort of optimizing your performance. Let's see. So yeah, generally worth noting, you tend to choose odd numbers for obvious reasons. You want to avoid a tie because this is a majority, this is a majority vote. So, just like in the Supreme Court, you want to keep the numbers odd. Another thing that you can kind of do, which is I think really kind of cool for a KNN, is you can adjust the weight of it. So, going back to our example here. So green won the label, although blue is actually the closest one. So you might say, just if I'm eyeballing this, it's not obvious to me that that red point should be a green, because it kind of feels like it might be a blue. And one way in which you can kind of adjust that is you can take a higher value of K, but you can weigh it differently. Oh yeah, sorry, everything down here, I'm not sure if you're able to see that distinction, but everything down here is green, everything up here is blue. Yeah, this is nightmare for colorblind people, I'm sorry. So you may weigh them differently. You may say, okay, well, let me weigh the ones that are closer proximately to it versus more heavily than the ones that are farther away. So that's kind of a nice balance where you're biasing towards the ones that are more immediate, but you're taking a higher sampling. So I think that's kind of a nice trade-off. The other thing to note is that distance. So I mentioned, most frequently you'll just take the Euclidean distance, but you can also take Manhattan distance, which is you just look at the vertical and horizontal axes, which if you're looking at specific features is not necessarily a bad approach. We also in lecture talked about using, didn't want to go ahead yet. We also talked about using KNNs for predictive regression as well. And so, that's the idea here of, as you're looking at a plot over time, you, or a plot overwards, you can you essentially take the average of the nearest points, and then you use that to generate a predictive model. So for K = 1, you just look at the point that's directly nearest. For multiple Ks, you just take the whatever the points are, and you take an average of it. And kind of the key things with this here are spheres of influence. So let's just look at one nearest neighbor. So here, this is, at this point, this is the nearest neighbor, this is the nearest neighbor, and then right up here is this neighbor's spheres of influence. At this point, this one becomes the nearest one. So any value up to here is the nearest one, and then immediately this one becomes the nearest one, and so on and so forth. Right? And so any value that falls within that gets assigned that prediction. And as you can see, much like with the classification, the higher the value of K, the more it averages out and the more of a smoothing effect you have here. So, okay, so I think that is KNNs in a nutshell. It is also 2 o'clock, so let me pause there. Let me stop the recording. And let's see if anyone has any last minute questions.